Okay, so first example on how to calculate the moment of a couple. So we have a pair of, well, we've got four forces here, but we realize that since these 20-pound forces here are acting parallel and opposite to one another, and these 30-pound forces here are acting parallel and opposite to one another, separated by distance, those each form a couple. So what we can do is we can figure out kind of what the magnitude of that couple of those couples are, and then combine them all into a single equivalent moment. Okay, so let's start with let's start here by expanding our axes notation here. I think it got cut off by cutting and pasting. So that's going to be x, that's going to be y, and over here we've got z. Okay, so let's start with the 30-pound one. So we've got 30 pounds, and so the moments equal to r cross, why did I say d? R cross f. And the distance there is 18 inches. So we know that the magnitude of that is going to be, pull up my handy dandy calculator here. So magnitude, 18 inches times 30 pounds. Or if we want to go for pound feet, 45. Let's use pound feet. Just because it's usually easier numbers to work with. So we need to define basically the directionality of that. We know, looking at this, because those two forces are acting, they're both acting in the y-z plane, we know that the only components of the moment generated by that are going to be in the x-axis. The question is whether or not it's going to be positive or negative. But we've got the positive x in here, and we know that based upon our right-hand rule, a positive moment would be kind of curling around up over the top, towards us, coming out of the page on the top, which is exactly the opposite of what we're seeing here. So that the moment caused by this, that's going to be a negative 45 pound-feet I moment right there. And then we've got the moments caused by this 20-pound couple. Now we know that the directionality of those forces is in the x directions. Negative x for this one, positive x for this one. But unfortunately, it's not quite as simple as this previous one, because it's not acting in a plane that is parallel to one of the prime planes. This original one we talked about, that was acting in the YZ plane because there was no offset between these 30-pound forces in the x direction. This one, however, we're acting in a plane that looks like this. So it's it's basically slanted there. So we're going to get a moment, but the moment that's generated by that is essentially, it's not going to be, the resultant is not going to be parallel to any of the axes in question, any of the prime axes in question. So to calculate that, basically, I'll just copy and paste a section from the notes here. So we kept the moment of the couple is going to be, again, the vector from one to the other crossed by the force in question. So essentially, what we can do is we can just define the vector from D to E, define that as our R here, and cross that with our force vector at E. Or we could do the other way around. We could define the vector from E to D and cross it with the vector at D. Either way works. Let's do the latter. That's kind of, relatively simple. All right, so what is our what's our R here? So R is going to be just our displacements. When we go from E to D, our displacement. So first off, what's our X displacement? Nothing. X displacement doesn't change there. Our Y displacement is next. So our Y displacement, so we're going from here downwards. So our Y displacement is going to be, actually I'll put 0 at I. Sometimes you wouldn't bother writing that, but for the sake of completeness, minus 9 inches J. And then we got our displacement from E to D, 12 inches here. And again, that's in the positive Z direction because, again, the Z axis was kind of defined based upon our right-hand rule. So that will go here. Oh, that's our 12 inches K. Okay, so we've got that. Well, we also need to know what our force is. So again, we're looking at the one from D, so that is acting in the positive I direction along the x-axis. So that'll be 20 pounds times I, and plus 0 J plus 0 K. I'm not going to bother writing it for that one. So I just need to take the cross product of those two things. So we'll use this method. It's relatively foolproof, I find. Okay, so R, starting with R, so 0 in our I, so negative 9 inches. Excuse me. Oh. 12 inches. Sorry about that. And then we've just got our 20 pounds. And 0, 0, 20, 0. All right, so we can go ahead and just look at these. So that cancels out to nothing. This one has some non-zero components, so we'll circle it. This one cancels out to nothing. This one also has non-zero components. That one cancels out, that one cancels out. So the result there, J times 12 inches times 20 pounds. I'm going to convert that to feet, pound feet. So that's going to be 20 pound feet in the I, sorry, in the J. That's J, not an I. And then that this one's slanted back, so we start off with a minus, but then we've also got a negative term and a positive term here, so minus 9. So I'm just going to denote that by switching that back to positive. Minus 9 inches. 9 inches times 20 pounds converted to 9 inches times pounds divided converted to pound feet, so that's 13.3. 13.3 pound feet, and that is in the K. So we've got basically figured out what the equivalent moments are caused by these two things, and keeping in mind that moment couples, they're free vectors. They can move around on the body in question freely, and they'll still cause the same amount. So basically, we determine we can have a single couple equivalent to the that would have moments equivalent to these two couples shown just by adding these two things together. So whatever couple it is would need to have a moment that is negative 45 pound feet in the I, plus 20 pound feet in the J, plus 13.3 pound feet in the K. And that's basically all we need. You may be asked to find the magnitude of that. But if you got the rectangular components and all you're asked is to define it, that's all you need. If you start because essentially if you have the rectangular components, that's enough information to fully define the vector in question based upon whatever it is you want. And then you're not futzing about with any angles. Whereas if you went and just figured out the magnitude of this, or you got the magnitude, you still kind of need to find the exact direction it's acting in, or the exact axis about which that moment would be causing this thing to try to rotate. And that's it's a bit of a pain in the ass. It might be useful to find that angle for some purposes, but oftentimes it's not necessarily necessary. So you might not want to bother. So that's about all we need for this question.